Hello class, welcome again. I'm your instructor, Dr. Mayas, and today we'll begin our first class in dynamics. This chapter is from chapter 12, which is the beginning of the dynamics course. As you know, this is a continuation of the statics. In fact, the static and dynamic books are split into two. You can buy the textbook that I provided you in the syllabus only for the dynamics, or you can buy the combined book or the book that combines both static and dynamics. As far as our concern for today, our goal is to go over the first few sections of the first chapter, which is concerned with the study of the kinematics of particles. More particularly, we'll begin with the rectilinear kinematics and the continuous motion. So our goal is to find the kinematics quantities and the relation between position, displacement, and velocity, and also see how we can use the calculus that I mentioned in the last lecture to help us find the relationship between position, velocity, acceleration, whether we are going from position to acceleration or from acceleration to position. The tradition that I will be using in giving you the lectures here is mostly will be PowerPoint and handwriting. So you will see me flipping between the two format. Probably didn't want to see me always in the camera, so I will turn this off because it's really not needed. So you'll just hear my voice and handwriting. Alright, so we'll begin with the study of rectilinear motion of particles. So what does particle means? Particle means is an object that does have a mass, but dimension is negligible. So when we look at an object far away from your observation, that could be considered as a point or a particle that doesn't have really dimensions, such as when we look or observe stars or a moon or a sun, we could consider that as a particle. Or when we look at an airplane flying from a far distance and we are only concerned with its position, velocity, and acceleration, we could think about that airplane as a point, or a car moving in a highway and far from our observation, that could be considered also as a point. So to begin with, rectilinear motion means object that move a straight line. So if we imagine or think about a particle moving in a straight line, right? Definitely we need to think about a reference point that define the location, or that can define how far is this object from that location. So we always consider a reference point. We call it O. So O is a reference point. And this particle, call it P, is moving in a linear motion, and the position of this particle as measured from the O, let's say, is given by R, right? Now remember, R is the position of the particle with respect to reference point O. So R is a vector, right? It's a position vector. Position vector measured from a reference point. It's a position vector of location of the point P at any time, if we are measuring this with respect to time, measured from the reference point. Now, when this particle, let's say after delta t, so if we consider that to be measured at t, and the object moves after delta t, the object moves by focus here, object or the particle moves by a magnitude of r t plus delta t, right? And it's a vector. That's the new location of the object. So therefore, it could have, if we call this is r1, and we call this r2, which is the new location of the particle. So we call this is r1 and this is r2. So the displacement of the particle, which is this magnitude, call it delta r, this is delta, is equal to r2 minus r1. Okay, so, and it's a vector, right? Now, since we are dealing with one line, and knowing that a vector has 3 components in Cartesian, and because this is one line, so we are not really concerned with other components. We're only concerned with one component, which is the direction along that line. So generally, before I put this in note, R is a vector, we said, and comprises of a component Rx plus in component form Ryj plus Rzk, where Rx, Ry, and Rz are the components, and this is the position vector. And if this is a time variant, then each one of them is a time variant, right? And as a time of function of time. Now, if this is since we're in the first few sections, we're only concerned with one-dimensional or rectilinear, then we don't really need to study that. So for simplicity throughout this work of this section, we're just going to refer to rectilinear motion by s of t, right? S of t. Why we're doing this? Because we only have one component, which is known here to be in the direction of one of these components here. So just let me just put this together in a simpler form. So this describes motion in one dimension, right? So such as if this is a reference, and this is my, call it S direction, that, and this is the particle. So this is the position of the particle as a function of time. And there is no reason I should say a function of time. It could be a function of any other thing, but commonly it's a function of time, since time is an absolute reference that we use always in measuring how objects move. Okay. Alright, so the position S of t, right? It could have a positive value or negative. A positive value means is measured or is the object is moving in the positive direction assigned. For example, here we must say that we have to decide whether this is a positive, whether it's a negative. So let's say always when the arrowhead pointing to a direction, that's a positive, and anything in the opposite direction is a negative. So a positive value means the object is measured toward the right direction, and negative to the left. And it's good to keep this as a common, especially when we solve problems. You will see most problem has this notation. So this could be positive, means it's or negative. Okay. Now, following the discussion we have done here, the displacement will come delta s, and it refers to the difference between the position of the particle at 2 different times, right? Now, the total displacement, or the total displacement that an object moved, is donated by S of t. total displacement. Now we have to be careful with that, because if I ask you find if a particle has been traced to move from a location 1 to a location 2, right? Let's say that, and I ask you find the displacement, then you say displacement is equal S2 minus S1, which is this portion, right? But let's say I have another problem where I have a particle. I started tracking it at position 1, and let me bring this closer so we can see it. And then this particle is moving. It stopped here at position 2, and then it's changed the direction and went back to position 3, right? Now, if I ask you what is the displacement between the initial and final, so initial is 1 and final is 3, so the displacement is simply S3 minus S1. If I ask you find the total displacement, total distance traveled by this particle, you're gonna tell me, yeah, this is the total displacement, right? But don't mistake this by saying, well, in the first case, the displacement is equal to the total distance traveled, because S2 and S1 are both in the same direction. The particle did not go back. But here, the total displacement or total displacement traveled by the particle is simply, in this case, for this case, is S3 minus S1, right? Plus this portion, let's consider that this is what happened, S3 minus S2, or let's say because of the positivity, so S2 minus S3, right? So because they should be positive, we are adding. Alright, moving forward, let's define the velocity. Well, the velocity is the rate of change of the position. So it's a rate of change of the position with respect to time, definitely. With respect to time, right? So what is the position? Well, let's go back to the general notation. The position is r of t, right? This is the position. Then the velocity becomes the rate of change, which is d r of t over dt equal v of t, right? So that is the rate of change, and these are vectors, right? All of them are vectors. Or if it's a rectilinear, so we can say, well, here's s of t, and this has become again v equal to ds over dt. So we must know s as a function of t to find out the velocity. So again, velocity is the rate of change of the position, and it's instantaneous, meaning suppose that we have a particle that undergoing this motion, and this is described as of t, right? So when we say find the velocity, we have to tell you find the velocity of an object at a time. So must be specified. Let's say if this is time 1, so then the velocity at time 1 equal to the derivative estimated or calculated at t equal to time 1. This is what it means, and that's how you can find it. So it's a tangent, right? It's a tangent, and or it's the slope of at that point. Great. Now later on we'll take some examples. I'm just now giving you the definitions. So instantaneous velocity at a time, let's say t1, is the ds over dt estimated at t equal to t1. Now, the average velocity, in fact, is the total distance traveled, which is, we talked about it, is s of t divided over time elapsed. Or we call it average, v average, equal s of t over what? Over delta t, time elapsed, or total time. I would say total time. Total. That's better. Let's focus on that a little bit. I'm gonna give you this. I know this is a little bit look like a high school problems, but this is a refreshment because we're gonna move and we're gonna move fast. If I give you this profile, right, and I ask you, and this is the particle movement, and this is at time 1 and time 2, and I ask you to calculate the average velocity of this object as it's traveling from t1 to t2, simply we're going to say, well, it's the total distance traveled, which is this distance, over the total time, which is t2 minus t1, right? It's happened like that, right? So if this is s of t, then it's s of t divided over t2 minus t1. So the total distance traveled by this particle, it's actually measured in the y-axis, so it's s2 minus s1, which is going to give me s of t divided over t2 minus t1. It just happened that it works. However, if I give you something like that, right, and say this is your s, and that's, sorry, this is your time, and this is your s, and that is happen to be t1, and this is t2. So what's the total distance traveled? Well, it is travel that distance and also travel that distance, right? And also travel that distance. So it did really travel the following. If this is S2, so S total is equal to this distance plus that distance, which is again S2, plus that distance, called S3, over total time. What's total time? Is in fact from here to here, T, T2, right? So my point here, you have to be careful and look into the problem carefully. Great. Now, moving forward, acceleration, or also deceleration. Acceleration is opposite of deceleration. Deceleration. Now, when a particle, so what's acceleration? Acceleration is a vector. Commonly we call it A, and it's the rate of change of the velocity with respect to time. Time. In notation, as a vector is equal to dv over dt, right? And it could be positive, that when we call it acceleration. It could be negative, we call it deceleration. So it could be a positive accelerate or a negative decelerate. All right. Now, this, everyone knows these. Now the remainder of this class is typically how to link the physics with math, right? And we'll talk more about that. And the way it's look like, so if we have a position function that describe how particle is moving, we can obtain the velocity by deriving it once. Derive. What would you get is the velocity, right? Or speed if it doesn't have a magnitude. Velocity is a term used typically for indicating that the particle has components. But in rectilinear, you will see me sometimes referring it to speed. So speed doesn't have a direction, it just is a magnitude. Time. So this is a derivative of that, ds over dt, right? And derive again, you're gonna get what? The acceleration. Something like that. I mean, arbitrary, just let's say like that, okay? Or in general, like this, any direction. All right, now if I want to go backward, right, what would I do? I have to integrate. So if I'm given the acceleration, to go backward I need to integrate. To go backward to position I have to integrate, okay? And going backward requires always initial value conditions. This is when you solve the differential equation, as we mentioned. But moving forward from derivative, we said, even there's a constant, or it will be the derivation of a constant is 0, so you don't need initial values to move forward from position to velocity to acceleration. But if you want to go backward from acceleration to velocity to position, you need this initial. And this is what I was indicating in the classroom, and we took some examples. So let me take some examples, and then I will refer to some examples also in the presentation and textbook. But believe me, look, follow my lead here, and I think you will be fine. So let's take some improvised example. Suppose that we have a car, right? And this car, I'm gonna use this dynamic terminologies now, is measured from an observer who is sitting at a point O. He's static, doesn't move, so this is a good reference point. So if you have a car, call it a P, and this car position is changing as a function of time. I will call it S of t, right? And where this refer the S positive. Example, given position of a particle P, B, S of t, where S of t, I'm just gonna give you as a function of time, t squared plus 1, meaning that, well, we started somewhere here, right? And it's parabolic, the way it's changing with time. Find velocity and acceleration at any time. Find the solution, right? Well, given S of t equal t squared plus 1, we know that the velocity or the speed by definition is the derivative of that position, which is equal to derivative of this equation 2t. And also the acceleration is the derivative of the velocity, the 2t, and that's equal to 2, right? This is a function of time. Now, let me give you another portion. Evaluate the actually, let me give it this way. Evaluate the speed and acceleration at time t equal to 2 seconds. Now we will be using SI unit mostly, and SI unit that concerns us is meter second, and for the velocity I failed to mention that it's meter per second, and for the acceleration is meter second square. So just to complete that, so this is I'm gonna assume this is in meter. I'm gonna say this is in meter per second, and this is meter per second square, right? So to evaluate, we need to know the velocity. So velocity is given by 2t, and then the velocity at time equal to 2 seconds equal to multiplied by 2, this is equal to 4 meter per second, and the acceleration equal to always 2, so the acceleration at time equal to 2 doesn't change because it's constant, right? Great. Now let's take another example. Given the acceleration of a particle b, a of t is equal to 2, and the velocity of the particle was 4 meter per second at time equal to 2. And its position at time t equal to, I'm gonna say 0, was 1. Find the position function and velocity function as of time, right? Oh, okay, as of time. Great. So what are we given? So I'm gonna dedicate this here for solution, and this is when you appreciate this is a math. So given for the first portion is we are given a of t is equal to 2 with velocity at time equal to 2 equal to 4, and position s at time equal to 0 equal to 1, right? What we want to find is we want to find the velocity. So I'm gonna flip this page and go to a new fresh page. Okay, now we know that the acceleration is equal to the derivative of the velocity with respect to time, right? Now distribute this or rewrite it. I can write this as following: a of t dt equal to dv, right? All what I did is think of it, I multiplied both sides. So I rearrange it, right? Now integrate both sides. Right? Now the integration, this is definite integration, which I'm okay with. And let me first use the do this integration as I don't know the initial conditions. So it will be a matter of later on substitute these initial conditions, which is I know them here. So I'm given a of t. A of t here is 2 dt equal integration of 1, this is equal to v, right, plus c, right? This is 2t equal v plus c. I know he's gonna say plus c, so plus c, another c, so it's still constant, so whatever you wanna put it, it's okay. So if you want me complete that, I can tell you this is c1, c2, c1, and then this can be written as v equal to 2t plus c. So that's what we get, right? Now the question is, how much is this c? To evaluate c, I need information about the velocity at any time, because we are given velocity at time equal to 2 equal to 4. So substitute this in that equation, right? So velocity at time equal to 2 equal to 4 equal to 2 multiplied by 2 plus c. So this is 4 plus c, then c equal to 0, right? So therefore the velocity as a function of time equal to 2t. As I found it. All right. Now let's find the position. To find the position from the velocity, we know the relationship that the velocity is derivative of what? Position, right? Right? Rearrange. And then take the integration of both sides. Right? Now, same way we did there, velocity is now given 2t dt equal to s, right? Or let's say plus c, or s equal, let's say c1 plus c2 if you would like. So this has become s. So integration of that is what? T squared plus c, right? Some constant. Now I use the initial condition. I will use the initial condition given that the position at time equal to 0 was equal to 1, substitute in 2, 1 square plus c, and how much was that? Sorry, this is 0 square plus c, and then c is going to be equal to 1. So therefore s as a function of time equal t squared plus 1, right? All right, so that's conclude the example. One thing you have to notice here, I just reversed the two examples. This example is in fact is the reverse of the previous example, and hopefully that gives you some insight and thinking of the relationship between position, velocity, acceleration in either direction of whether it's integration or derivation. Now One last item is sometimes we have special cases where the acceleration is held constant. In such a scenario, if we were asked to calculate the velocity and the position from a constant acceleration, then we can still conduct the method we showed you, which is integrate both sides of the derivative to obtain the velocity, right, and position, and that will lead you to a special cases. And these special cases, in fact, are very popular, especially when later on we'll deal with problems that involve constant acceleration, such as an object falling in or moving under the gravitational constant, which is 9.81 meter per second, and that reduces into three common problems, or three equation of motions. So assume that we have a constant acceleration, AC, right? So what we can do is integrate both sides, because AC is equal dV over dt, rearrange and take the integration of both sides measured from an initial value, or time we already assume it to be starting from 0, just for the sake of simplicity. And then this will give you an equation of motion where the velocity at any time equal to the initial velocity plus AC, the acceleration multiplied by time. Furthermore, you can find the position from this equation, and again you V equal to ds over dt, rearrange and integrate, and this will give you the position at any time equal to initial position plus the velocity initial multiplied by time plus half ACT squared. Now from these two relationships, we can also extract a third relationship, which is obtained from the chain rule, and I'll talk about that in some other time, and that will provide us with a redundant dependent equation, I would say, where the velocity and position are related without any involvement of time. So velocity square equal to velocity initial square plus 2 times the distance traveled by the acceleration. So keep that in mind, as later on we'll dwell and talk more about that. I will introduce you to the chain rule, and we'll see how is that all happen. Alright, well, this is it for today. I will see you next lecture on Tuesday, and if you have any questions, please ask me during the face-to-face meeting.